Welcome back to the class. We're going to start the exercises now. So we have two exercises. So the first one I will go through together with you. The second one, we'll go through the question and analyze the question, and that would be your homework. So let's go to the exercise 3.1. Okay. So in exercise 3.1, we have a styrene production reaction, and this reaction is the dehydrogenation of ethyl benzene, meaning the raw material is ethyl benzene, and we will have styrene as the co-product, and byproduct is hydrogen. What you need to do is you have to create the stoichiometric reactor model, meaning here is R stoich, to be run isothermally. It is isothermal reaction, and you have to use Bing-Robinson as the property package, and the feed stream is, of course, is a pure ethyl benzene with the flow rate of 217 mole per second at the temperature of 880 Kelvin and pressure of 1.378 bar. And it is mentioning here you have to specify the feed composition as a mole fraction. Of course, mole fraction for ethyl benzene here is 1 because it is a pure ethyl benzene. So isothermal reactor, this is a reactor specification. Pressure 1.378 bar and the temperature is 250 degrees C. So fractional conversion given here is 0.8 of ethyl benzene. So if you're having those information, then we have to analyze the problem before we solve the problem. So hydrocarbon system, and this justify the selection of Bing-Robinson. Why Bing-Robinson is suggested to you, right? Because it's a hydrocarbon system involving ethyl benzene, styrene, and also hydrogen. And in this question, the conversion of ethyl benzene is given to you is 0.8, right? And based on this point, you know that you can actually use R stoich to solve the chemical reaction engineering problem. If you use R stoich, remember just now, R stoich can actually allow you to perform the calculation of heat of reaction as well as the product selectivity. Okay, now let's solve the problem. Of course, you have to create a blank simulation as usual. It include the components involved and select the property method, generate the property, and save the file in backup format. Right. The components involved here is there are three. We have the raw mat, the ethyl benzene, and we have two product, styrene and also hydrogen. So in terms of property method, as mentioned, you have to choose Bing-Robinson. Just to remind you, if you don't know which steps to go after you include the list of components, you can just click next. Then you'll be guided to a page for you to select the property method. Just use or just fully utilize next if you don't know which page to go. But if you have familiar with Explain Plus, I think shouldn't be a problem. You can actually use a navigation pane here to include those required information. Okay, so once you have done that, you have to shift to the simulation environment and construct the flow sheet. Obviously, you have to choose R stoich, and yeah, the icon here is all representing R stoich. I will choose this first one and connect to the stream. We have one inlet and one outlet, and we name the reactor using the proper convention. So R101 here, I have put it as the name of the reactor. Once you have the flow sheet, of course, next is to include the feed specification. Here, you are asked to put or to include the mole fraction. What you need to do is on the left column, you have the temperature, pressure, and then you put in the molar flow rate, 217 mole per second. And on the right, okay, on your right, you have the composition. So you have to choose mole fraction, and put ethyl benzene as 1 because it is a pure ethyl benzene. Okay. Next would be to include the reactor specification. The informations given are temperature and pressure. Just put in accordingly temperature and pressure. Right. And next, you'll be having this the reaction details. You have to include the reaction details like the chemical equation at least. So in this case, you are having 1 mole of ethyl benzene, and you can produce 1 mole of styrene and also 1 mole of hydrogen. So just go to reaction tab, then click new, and you will have this page turn up. So reactant section is on your left, okay, and product section is on your right. Remember, stoichiometric coefficient for reactant will be always negative, and for product will be always positive. Okay? And it must be included based on a balanced chemical equation. That means the atomic balance and also the molecular balance, okay, on the left and also on the right of the chemical equation. It must be balanced. Okay? And other than the chemical equation, you have to state also either the molar extent, so this is the extent of reaction, or the fractional conversion. Given in the question is the fractional conversion of ethyl benzene, and it is 0.8. Just put it accordingly. So once you have included the required information, if you would like to perform the heat of reaction calculation, you can go to this tab, heat of reaction. It's under the same page, okay? Under the same page, that means it's under the block R101 under setup. So you have this heat of reaction. So you have to opt report calculated heat of reaction and set the reference compound. So reference compound or reference component here must be your one of your reactant. So we have only one reactant, which is ethyl benzene. So just select accordingly. Okay. So once you have done this, just click next and you'll be guided to a page saying that all the required informations are in, and you can run the simulation and check the results. So under the results tab, okay, under the block, and you have the results tab. So you can have the mole balance and also mass balance. What is the molar flow rate in, molar flow rate out, and what is the enthalpy for the inlet and outlet. Okay? And based on the differences between the inlet enthalpy and outlet enthalpy, you can have the heat duty here. So you can check under the summary tab. So you have the heat duty and also the vapor fraction, meaning it is a vapor phase reaction in this case because 100% vapor. And I think under the reaction tab, you can go to the reaction tab here, then you have your heat of reaction given to you, and also the extent of reaction also will be calculated accordingly, right? So the heat of reaction is about 28,127 Kelvin per mole of your reactant. Okay. Of course, other than this result, you can also have the stream result. Okay. That means the distribution or the product composition can be seen over here. Okay, I think that's all for exercise 3.1. It's a simple exercise. We'll stop here for a while before we proceed to analyze the problem of exercise 3.2 so that you can work accordingly later on at home. Thank you very much.